So now let's look at the big O of quicksort. So I'm going to bring up an array like this. And when we run pivot, it brings us to a point like this. So the first thing I want to point out about this is we didn't have to create any new items here. We just move things around within the same array. So this is different than merge sort that creates new items and therefore doubles the amount of space that it takes up in memory. With this, you are working only within the original array without duplicating any data. So from a space complexity perspective, this is O of 1. And this is an advantage of quicksort over something like merge sort. From a time complexity perspective, in order to move all of these items around like we just did here, that was O of n, because we had a for loop that went from the beginning of the array all the way through to the end. And if you look at how many times we had to do this, this was 1, then we did it 2, 3. That is going to be log n. So what we just did here is O of n times log n. And we'll look at this on the graph like this. It's much better than O of n squared. But the problem with this is what I just showed you is actually the best case for quicksort. The worst case is not O of n times log n. So now let's look at the worst case. The worst case is if you have already sorted data. So if we take that first item there, we make that our pivot point. We're going to compare that to all the other items in the array, and that is not going to move. So I'll color that in green. But what we normally do with quicksort is we run quicksort on all the items on the left of it, all the ones that are less than, and then run it also on everything on the right. It is that splitting of the array that makes it efficient. But in this case, there are no items on the left. There are only items on the right. So there is no splitting of the array. And the same is true when we look at 2. We compare it with everything else, and there are only items on the right. And for 3 as well, and so on, all the way to the end. So in this circumstance, this is actually O of n squared. That is our worst possible scenario, and that is what big O measures. So our best case or average case would be O of n times log n, but our worst case is O of n squared. So if you have sorted or almost sorted data, this is not a good sorting algorithm. But if you have random data, this is an excellent sorting algorithm. It's very fast, and the space complexity is O of 1, which is better than merge sort. If your data is sorted, it would be better to use something like insertion sort, even though that's O of n squared is its worst case. If you're using sorted or almost sorted data, it is very efficient. It actually runs at O of n. Okay, and that is our overview of quicksort, big O.